Okay, welcome to lecture 26 of PDEs. Today we'll continue solving Bessel's equation on, the wave equation using separation of variables on a disk. In particular, when we go to our cylindrical coordinates, we have the Strommel problem and Bessel's equations that we were doing. And the last time we almost finished it. We basically got to the fact that you could write the whole solution as an expansion of your time part times the Bessel function that solves the Bessel equation obeys the boundary conditions radially, times cos, which is the even mode, okay, and plus the second part, which is exactly the same, times the sine part, which is our odd modes. And then we started decomposing the problem, and we said that we had to find, in this decomposition you have constants in front for your even modes, that goes with cos, and constants for your odd modes, and you sum over the nodes that go around the axes in phi, the number of times you get 0 there, for both the odd and the even sectors, and you sum over the radial nodes that go out, which is indicated by m, which counts them. Okay, and then the frequencies that will appear in these oscillations are actually set by this constant k in m, which is the mth node of the kth Bessel function. Okay, so you were getting your frequencies out of the geometry. And then I said we should basically, in order to solve the problem and write down the final solution, we need to find these constants A, E, AO, B, E, E, B, O from the initial conditions, and that's what we're going to do today, basically. So what we had is we have our initial conditions, and the way we find these constants is we're given this initial condition in red, and if we just substitute, and if we compare it to the expansion up top here, and we substitute t equals to 0, we simply get that this function we should be able to represent in the following way, where these constants are known. And one comment is, this is where that completeness of the solutions to the Strommel problem come in, is that you can unambiguously and uniquely represent this function in terms of this basis, provided you have actually kept both sectors and not done as the textbook did, lost your sine sector. Okay, so any arbitrary function that's written in this way can be represented in that way, and you're assured of doing so. And in fact, what I'm going to do now is simply provide the prescription of computing what A, E, and AO, which are constants. Okay, and in a similar way, you can have your derivative of your psi function. You simply differentiate this thing, put t equals to 0, and then you can expand that thing on the same basis, just with different expansion constants in front. And you can use then also similarly, in a very similar way to what we determine the A, E, and the AOs from our initial profile, we can get the B's from the initial profile change. And so let's do that. And the way we do that is we basically take our initial condition and we multiply it with the basis functions in phi and in r. We add our little area element, which is that r, and then we integrate over the whole volume. And let's examine what this gives us if we substitute the initial condition in for psi. So we're simply going to put the series in there. And the moment we do that, and we remember we're going to need the following identities. Remember, the integral from 0 to 2 pi of sine and cos is 0, and the integral from 0 to 2 pi of cos is equals to the delta function. In other words, it's 0 if n is not it's 0 if n is not equals to p. If n equals to p, it's pi, provided p is greater than 0. Okay? If p is equals to 0, then the thing is just the integral from 0 to 2 pi, which is 2 pi. So there's a special coefficient if p is equals to 0. Okay, so let's just do that now. So in general, what you get once you've substituted the series for psi, which I gave up there, into this integral, is you get basically, and you, because the series is assumed to be converging, which it is, provided the actual function obeys boundary conditions that you require it to behave. I mean, in other words, you need to get a psi where at your boundary it's 0. Okay, so then you can switch the summation and integration. Okay, so what I've done is I've basically taken the sum out and the constant out, and written everything, the remaining integral, over basically the functions that are left here. Okay, so what happens then is this integral over phi is easy to do just from the above identity. It's simply, if p is greater than 0, it's simply pi times delta np. So we can do that integral. And then what we're left with is this expression, right? So the delta function over np ensures that n, provided it's greater than 0, provided p is greater than 0, it ensures that n is equals to p. So I've replaced n with p over here, and n with p in the zeros as well. And then what we have is this remaining infinite sum over m, over the actual zeros for a given p, and this integral, which in order now to find a, we're also going to have to compute. Okay, just one thing before I go further. If p is equals to 0, right, then you have the case that this integral is just the integral from 0 to 2 pi d phi. So instead of having a factor of pi, you have 2 pi coming in there. So the 0 case is slightly different. And then, but you also have this integral remaining. And so the next step is basically to have a look at how we evaluate this integral, and we get to learn a bit more about Bessel's functions. Okay, so that integral, there are various ways. If you start from scratch, if you know nothing about Bessel's functions, there are various things you can do. The first one is you know that J, write down what you know. So you know that J solves the Sturm-Liouville problem. Okay. So it's a valid solution here for a given P. And for lambda, where lambda, okay, it's a Sturm-Liouville problem. In other words, it solves this equation. It has these boundary conditions. It's 0 at R1. And the lambdas that we have are known. Okay, so we know that's true. And so we immediately know that this thing obeys, the eigenfunctions in your Sturm-Liouville problem obey an orthogonality condition, provided you have the right weighting function. So here you have to be careful. You have to make sure that this integral has the right weighting function in order to use that orthogonality condition. So let's just do it. Let's define our inner product. Remember, we did it associated with the Sturm-Liouville problem as the integral over the domain of the basis functions times w of x, that weighting function, and here w of x is simply r. So okay, so this thing basically indicates that this integral up here is an inner product of the two basis functions. Okay, and so we have from that lem, I think something like the third lemma I proved in about the Sturm-Liouville problem, just using this operator as well as the boundary conditions, and not even knowing anything about the zeros, that this identity held. In other words, that the difference, the product of the difference of the eigenvalues multiplied by the inner product of the two basis functions is equals to 0, which means that basically either the eigenvalues are equal or that the basis functions are orthogonal. Okay, and so this thing directly implies that either the basis functions are orthogonal if q is not equals to m, in other words 0, or this thing is non-zero if q is equals to m and it's equals to some constant, because it's an integral, right? So you're going to get a number. So and it's equals to some constant. And it's now this constant we actually want to calculate. Okay, and that constant is just this integral over the Bessel function squared. Okay, so now you want to compute this integral. And that's what I want to say. There are various ways of playing with Bessel functions. There's a tremendous amount of structure in the Sturm-Liouville problems. I like them for that reason. And so there are methods of planing. You have that generating function, you have the series expansion, you have the fact that the differential equation it obeys is this one. And then you can start using sort of parts of that information to try and evaluate this integral. And often the first thing I do is I go back to the differential equation itself, because there's a lot hidden there. And if I do that, I can basically show that this is true. Okay, so what I did here is I basically multiplied this whole equation through by r y prime r, okay, divided by 2. And then the first term is equals to ddr of ry prime r squared. Okay, so it's a derivative of that whole thing. And then you can add another term, and then you get something, right? Which is also, you can write as a derivative part. In other words, if you differentiate this, if you differentiate this guy and use this equation to substitute for that term, and then you add this thing back to it, what you get is this. So I've actually, when I use that, I've actually written this r y squared as a complete differential. And so the integral, working out the integral, is actually analytic and nice. And so we can actually say that the integral Cp is 1 over 2 lambda associated with the eigenvalues times basically this thing evaluated at 0 and r1 on the boundary plus this thing evaluated at 0 and r1 on the boundary. Okay, and so let's now do it. So first let's look at the second term, right? The second term, and let's look at it at the boundary r1. That's easy because at r1 you simply have jp of k pq, and that's a 0 of jp, so it vanishes. Okay. Okay, so it vanishes at r1. At r equals to 0, jp, if p is not equals to 0, is 0. If you just look at the properties of all the functions. Okay, so if p is greater than 0, it also vanishes. If p is equals to 0, right, so p is equals to 0, you have an r over here, and so even that j0 at 0 is 1, the r over here goes to 0 and it also vanishes. So this term is completely gone. And so what remains now is to evaluate this final term. At r equals to 0, you have an r there, it vanishes. So the only thing you're concerned about is evaluating this thing at r equals to 1. Okay, and so just check here. The one thing I've done is over here, I've got ddr of the Bessel function p at r. And what I've got here is a prime, so that's a complete derivative. So I've basically this thing, so the ddr over here is simply j prime times the argument dr, so that's where this extra factor of kpq over r1 comes from. Okay, and then I evaluate that at r1, and I am left with this expression. Okay, so, and that expression you can use. It's simply the derivative of the Bessel function p at the zeros p. And okay, squared. And if you look at the book that they've got, so this is fine to use because you've got the series, you can evaluate it quickly. The textbook over there had a different expression, okay? And that different expression actually comes, you can actually derive from this expression. And the way you derive it is, in addition to having all the properties that I mentioned earlier, the Bessel's functions are related to each other simply, and you can intuit that from the fact that you have this generating function, right? They've all come from this big rule that you have, that they are the series expansion of e to the x over 2 times t times 1 over t, okay? But another way of, so the Bessel functions of different p are related. And to make this relation explicit, what we do is there are recursion relationships, okay? So the following thing is true. J of the Bessel function of order m minus 1 plus j of m plus 1 is equal to 2m over x jm of x. And another one that's sort of often used is just the difference of the two is equals to that. And you can look at that, and the way you can prove it is you can simply go to your series representation of your Bessel function and write down the series representation for all of them and prove that it vanishes. Okay. And so if you combine these two, you basically get that the derivative of jm of x is equals to m over x jm of x minus jm plus 1. Okay, and so if m is 0, you have that ddx of jm of x, which is what we have over here, is simply equals to minus jm plus 1 of x. And so this is the expression that they have in the textbook, is that or rather, a special case of this expression is basically that this factor that is basically the norm of the Bessel functions is simply J1 of, it's basically the Bessel function of order p plus 1 evaluated at the qth or 0 of the Bessel function of order p. Okay. So it's definitely non-zero because you know the Bessel function, no two Bessel functions have the same zeros. So that's also, so this thing is basic, this expression is useful in the sense that you get that insight, that you know that these factors C are always non-zero. Okay, so anyway, so now we have the factor C, and we can go back to our problem because we've computed the integral, and then just write out the full solution, or rather write out what these A's and B's are. And so here we have that integral that I was computing just now. And so we can actually write it out. If you have 0, so the 2 pi factor is in here, divided by 2, that integral is now evaluated to this, and that R1 squared is also there. Okay, so you have a linear relationship, and this thing is a constant, right? So you have your coefficient is, the way to get your coefficient is work out this integral if you're given psi, divided by this factor, and you have your coefficient for 0. Okay, your coefficient for any p is very similar, just with this factor of 2 coming in. Okay, and the odd sector, you can now, in other words, we've gotten all these coefficients is what we've worked out. The odd sector here, the way you get those is you simply multiply your initial condition with psi now instead of that. And it proceeds very similarly, right? If you substitute in the series for the sign, you keep the only non-zero integrals is if you have p equals to n, and then over phi, and then your integral is pi. So you actually just choose out this part of the series, and you only have the case where p is greater than 0, and so you can find that once you've computed this integral, your odd coefficients are just this. Okay. And you don't have a special case because with the odd cases, p is always greater than 0 because p equals to 0 just vanishes. And then to get the b's, you now once again go and do exactly the same thing. You have your initial condition, which is your initial basically velocity profile. You know what the expansion is, and you once again construct a similar type of integral, which I'm going to call k, right, of the initial velocity profile times these basis functions, each of the 4 different types, and then you can actually get the coefficients out. So you can you again have a case where for the cos sector, if p equals to 0 is special. So you have this b equals to the integral divided by this factor, and you have the general case where the p is greater than 0. It's simply you get this frequency factor coming in, but then it's exactly the same thing as what you got for the a's. Okay. And similarly with the odd sector, you take your function, you multiply it with sine, you integrate over it, you use your orthogonality condition for your Bessel functions, and you get that the b's are related to the integral in the following way. So you've basically got now a way to get all the coefficients, and then you're done getting your solution. A couple of observations. If you have, and that's the example we'll do next, but I'll just want to keep this slide here so that I can talk about it. If you have a function psi, let's first say, suppose your time derivative is 0. In other words, you have a stationary profile. In some sense, you've molded the shape of your drum that it has this thing, and then you just let it go. Then the moment that thing is 0, then all your b's are 0. Okay. The moment you have, suppose you start with no profile but a time derivative, then you only have b's. Suppose you start with a function that has no angular dependence. Okay. So in other words, if you take, it's a function psi, and that's the thing that they did in the textbook. In an example, I'll do detailed next time. In other words, psi is a function only of r. The moment you take an integral of cos p phi, it vanishes. So the only integral you have, or sine p phi vanishes. So the only non-zero thing in that case are these coefficients. So a0, where p is equal to 0, q. Okay. Suppose now you have an initial condition that looks like a wedge. So suppose you have like that your initial condition is non-zero only if phi is less than 3/2 pi. So only if phi is less than pi/3 and greater than minus pi/3. So you have this wedge over here. And suppose it's symmetrical about the axes. What do you think you're going to get? Which coefficients are going to be non-zero? Okay, so I don't want to poke you, but what I want to say is there's a direct correlation between what the function looks like and the coefficients that you excite. So if you have, like, suppose you have, I wonder if I'm not going to have a chalk, and my microphone's not going to reach. But suppose you start with a circle, right, with an initial condition that looks like that, and is symmetrical about this, the x-axis, right? So then it's effectively an even function. Okay, so it's going to be expanded in causes. So when you take the integral of this thing, all your sine components will vanish. Okay, so then all your O's, your AO's will go. Now suppose you were to have this case. Okay, so you have your wedge pointing up. So then in that case all your cos components will vanish. Okay, so the shape of what your initial condition is or what your initial function is like would make a tremendous impact on what the answer is like. Now suppose you were to have something that looks like that. Okay, then you'd have a mixture. You would have both of them appearing. And if I find a problem like that, what I would do is I would change my coordinates that I have a symmetry on the axis so that I have fewer integrals to do. Okay. This you see again and again. I'll first going to do the example and then I'll tell you more stories. But this idea that the modes that you excite is directly correlated to the geometry and that there are clever ways of choosing it is what I want you to know or to remember. But in order to do that well, never take a shortcut and try and do something clever there. Always write out the full answer like I've done up top there, and then actually choose your coordinates and then do the integrals to make sure the functions actually vanish. Okay, because what tends to happen there is that thing is basically going to excite all the cos modes. If you have something like this, so I want to draw something now with sort of threefold symmetry, right? It's still even about the axes, so there are going to be no sine modes. But the lowest mode it's going to excite is n equals to 3. Okay, and then it's going to tend to excite n equals to 3, n equals to 6, n equals to 9, because it's all going to capture the symmetry that's in your initial condition. And so you can get a feel for it and you can sort of guess what the answer is going to be, but always do the integrals, otherwise you do make mistakes. But it's kind of fascinating. So that's what I said, your initial condition and how, in fact, suppose you consider a flat membrane, right? And then you consider your initial condition, say, as somebody's hit the drum like once. Okay, so that's basically going to give you a d psi dt. So that's why I said where you hit the drum is going to make a tremendous difference in the frequencies you excite, right? If you hit it in the middle, you're going to excite your fundamental mode. If you hit it here on the sides, you're going to normally excite the n equals to 2 mode. So you're going to have the frequency associated with that. If you have two sticks, whether you hit it like this or whether you hit it like that also makes a difference. So like if you hit it like this, you're going to excite n equals to 2 modes because it's the one that I showed you where it goes down. If you hit it like straight on, then you're going to double it. So you're going to start exciting n equals to 4. Okay, so your drumming skill, if you want to do it in a mathematical way, you can actually work out where you want to hit it and what frequencies you actually want to excite. So let's just now do the simplest of examples explicitly. Okay, so there's the series, and we're going to start with a stationary profile, which basically means the time derivative is 0, okay, which immediately gives us the b's go to 0. And we're going to say, initially I have a cone-shaped profile. In other words, I've taken my drum, I've put my little, my speaker, I've pushed it up with like a dowel or a speaker. Okay, so I have a cone-shaped profile, and what that is basically is that psi 0 at time t equals to 0 of r and phi is just this expression, right? So when r is equals to 0, I've chosen the height to be exactly the diameter of the drum. So it's just a specific example. So I've chosen r to be r1. If r is equals to r1, then the thing is 0. And that's required because your initial condition also has to satisfy the boundary conditions. Otherwise, if it doesn't, you're still going to get an answer. but you are not going to get, well, if it doesn't satisfy the boundary conditions, one, you've posed an inconsistent problem. With this technique, you'll still get an answer which is the best approximation had your initial condition actually satisfied the boundary conditions. So it's fine here, but it's just to have a consistent, mathematically well-posed problem, you have to have psi that satisfies the initial condition. Okay, so now you have R equals to R1, and you go about almost systematically, you compute this, what a lot of people call these things overlap integrals. It's simply how your initial condition is projected onto your various basis functions, which I showed you the last time. So you basically compute this integral, okay, and you know it's just as I said, previously, J is a function just of R, you just have a function of R here, so the cos of P phi integrated from 0 to 2 pi is just 0 unless P is 0. So you immediately get that all these coefficients are 0, so the A EQ is 0, P is greater than 0 by the angular integral. And similarly, if you look at the odd functions, in other words, if you times that thing with sine instead of cos there, they're also all going to be 0. So your odd functions vanish. So the only non-zero coefficients we actually have to compute is this one. So it's A 0Q times I times that thing. And then once you've got those, you can write your solution down, okay, in this manner, right? And so you have for each mode, it's going to oscillate on a frequency that we already know, and it's going to have that shape. So we're basically going to have, and there's no angular dependence because it's all of those coefficients are 0. So you're basically going to have your drum shape, and it's going to go bloop, bloop, bloop in a certain way. But there's going to be you can't excite modes that weren't supported by the initial geometry of your initial profile if you have a linear problem. Okay, so now the rubber always hits the road when you have to compute the integrals. And I've spent much of my life computing these integrals. So you have to compute this integral, okay? There are various ways of doing it. One, you can do it numerically, right? Because you actually know what the Bessel function is. You have a very nice expression for what it is in terms of an integral. Okay, so you can try and play with that expression and compute it. What is true is that there are a whole bunch of people, in the case of Bessel functions, that have used Bessel functions when they study diffusion through circular membranes, or like cylindrical membranes, because it always appears in cylindrical coordinates. And so in the 1960s or 1970s, there was actually several people that worked out that all integrals of the form R times a polynomial of R times the Bessel function can be found. Okay? And there are closed form expressions for those things in terms of Bessel functions. You can see that, I mean, you can actually work it out sort of at least not intuitively. You can't get a nice answer. If you were to simply substitute in the series expansion for the Bessel function into this integral, you could actually work it out term by term yourself if you wanted to. That's not what they did. They found a cleverer way of doing it. But anyway, there is the sort of the paper that I found that was the nicest, because I started looking yesterday. I've played with Bessel's functions before because I did modeling of water into a borehole, actually as my master's thesis. And in order to compute the flow of the thing, you get a partial differential equation for more than one variable in cylindrical coordinates. One of the equations was Laplace's equation. So you can separate it and you can actually reduce it to Bessel functions. So I spent a lot of time looking at the identities and stuff. And that's typically problem specific. Once you get a problem you want to solve and you reduce it to a Sturm-Liouville problem, you make those functions your best friend. Okay, and another functions that are really nice to play with are Legendre polynomials as well that appear in quantum mechanics. They appear whenever you have spherical symmetry. So anyway, Okay, but there is a result that any integral where f of r times a Bessel function of any order, where the argument is r times alpha, has an exact solution. Okay, and what I did to actually evaluate these integrals is I cheated, because Mathematica actually had the correct exact solution. So here's one thing, is I basically asked Mathematica to integrate it, and it gave me, but I'd already never do that. Never just trust what Mathematica says, because there are mistakes in these functions. They've done a very good job, but they sometimes don't define the variables exactly as what you expect them to do. So always make sure you understand how the integral is computed before you use Mathematica. So it fortunately turns out that Mathematica gives you the right answer. Okay. Also, the lowest ones here you can actually get by integration of parts, right? And because if you integrate this thing by parts twice, right, you once again have it in terms of its earlier, lower derivatives from the differential equation, and you can get rid of this thing by integrating by parts. So, yeah. But anyway, what Mathematica told me once I implemented it and checked, or not implemented, I checked that they had the right formula, and I simply asked it to integrate this, is that this integral, the overlap with the Bessel function with the first zero is huge. Okay? Then the next one gets smaller, and the next one gets smaller, and then here are the rest. The thing that becomes problematic is it's not here you have one getting bigger. Okay. But anyway, this series will converge. You're assured that it will converge if you obey the boundary conditions. And it's a representation of this function. And so you now actually have your whole solution. Each mode oscillates with a different frequency. And that frequency you can get in the slides of the previous lecture, because I actually gave them to you. And so you can actually write down what the thing looks like. One check whenever you do something like this is, and that has caught you in some of your problem sets, is in particular the heat equation one, is you need to actually, once you get these coefficients, plot them to make sure your function approximates the initial function effectively. And so I actually did that. Okay. And this is what had happened. I actually wanted to plot the wave, but I ran out of time. So I didn't do that. But just the initial profile, I did the initial check. So this is the initial profile, right? It's just a cone, and I've just shown the positive, basically the profile in R. And what I'm now going to do is I'm simply going to have the sum up to a certain end. So if I have add one mode, this is what basically this is just the lowest order Bessel function at the zero. Okay. If I add a second mode, that's what the approximation looks like. And if I add a third mode, the approximation gets better already. So you know that basically these top three is like the minimum if you actually want to get an idea of what the drum is going to look like. And in fact, how the different frequencies here are going to interplay. But for good measure, keep going until you achieve a pre-decided accuracy. Okay. The thing will always be bad here at r equals to 0 because you effectively have a cusp. And so you have a discontinuity. So the series will not converge very quickly, but it will converge. So there's 5 modes. Then it makes smaller, 6 modes, 7 modes, 8 modes, and eventually it will become exact. So always check your initial projection. And then what I wanted to do, but didn't get time to, I'm sorry, is I actually wanted to, I have the basis functions, I have these coefficients, I wanted to see what happens when you add the cos omega t term, but I will, if I do that, I'll actually show it to you. Because I myself don't know, right? Because you have this profile and it's now going to break, right? Initially, the whole thing is going to sink because cos at t equals to 0 is the maximum, right? So the whole factor is going to like come down, but some of it is going to sink faster than the others. The dominating thing will basically be, the dominating thing will be that mode, right, that frequency. But the question I wanted to sort of answer was this the frequency of the 2 mode is almost double, not quite the frequency of the first one. And they are never multiples of each other. So it's not clear how you get back to the point where all of them are 1 again. Okay, so my prediction is that I'm never actually going to get a spike again. I'm just going to get a drum that basically does this in the fundamental and does other weird things on top of it, and I don't, unless I plot it, I don't know. So that's it. Okay. These things you get fit with if you use them, right? A lot of the reason I can do this so easily is because I've played with them a lot. And I've had research problems on them. Another research problem I had that was actually very fascinating is that anything you can like decompose into this they call this a normal mode decomposition. In fact, this expression up here is the general normal mode decomposition of the wave equation on a circle, right? And these things over here, these are the basis functions which are basically referred to as the normal modes. Okay, and they're also the ones that you multiply with to get the projection right. So that's a normal mode decomposition. So anything you can do, you can decompose into that. Even if, like for example, let's look at the classical example that's closest, the sun. Ball of fluid, it has pressure, it has temperature, it's in hydrostatic equilibrium. So you have your temperature field, your pressure field, your density field, because it changes in density as you go across. And you can write down the equations that involve a lot of Laplace equations for what leaves this in equilibrium. And you can actually solve it analytically. And each of the things you can, because you can do separation of variables, and each of the whole solution you can actually write down in terms of not Bessel functions, but the ones in 3D. And express what the sun will vibrate like in that. And it has frequencies that enter into that thing. And those frequencies actually depend on the zeros, the geometry, but they'll also depend on how your density is distributed in your star. And so you can actually look at the frequencies and then adjust your model so that you can get a measure of the density of the star. So you can, how the matter is distributed in the star, whether there's like iron or what is in the core, you can sometimes infer from the frequencies itself. And it's a very, very well studied thing. If you look at the sun, they actually do observations of the frequencies. And you can see all the modes coming up to an incredibly high mode. It's a beautiful, beautiful, beautiful study. In a similar way, you can do the same analysis of the moon. And they find that the moon is actually vibrating. And so then what I must say is, these frequencies come from the analysis. If you knock the object slightly in any way, you tend to excite those frequencies and see them. You can do the same analysis on the moon. They know that one of the frequencies are ringing with a higher amplitude than what they thought, right? Because usually you knock it and it dies down. And the one theory is that that's still ringing from when an asteroid hit it a certain while back. Okay, so you can learn things from these frequencies about the structure, about the history, in some sense, modes that have been excited and not excited. And so what I did for my PhD thesis was a neutron star. You also have frequencies in. And what is interesting with a neutron star, if you look at it, the first model is just it's a ball of gas or fluid. and you can work out its frequencies. And you can also work out the modes. And so the modes have like oscillation modes that is normal like this, but there, because it's a fluid, you can also have modes that like flow. And so the one thing was that if you have a rotating neutron star, you could have a certain mode that becomes unstable if you can give off gravitational radiation, and then actually distorts the star. And they thought that that would make a signal that you can look at neutron stars for. And so I spent a lot of time actually working out the frequencies, how big these modes would go, and playing with a different set of Bayesian functions, which also solved the Sturm-Liouville problem. And I basically had all these integrals to compute, and I had this list of identities, and you just keep going until you eventually get the whole model of the star. And I managed it, and you then change the thing from something you don't know to you can really like get into knowing like if you push this frequency, it's going to get those other frequencies excited. It was fun. But anyway, you get fit with these Sturm-Liouville things. So if this looks intimidating, they're just straightforward steps to actually working them out. And I've tried to outline some of them here. For the purposes of your test or exam, I'll guide you along. I'll say, like, prove this, prove the next thing. But when you start with a fresh problem, you don't have that. And then sort of knowing what to try and sort of writing down all the tools you have and then saying, oh, let's dig a little bit this way, see if I can get something there. To me, that's the fun part of science, right? You have the unknown. And it's also the way you develop your skills. You get really fit because it's like, oh, I've computed this integral 1,000 times. And I don't want to do another one. And in fact, then sometimes even that frustration is useful, because what happened was you can actually, and this is what these people did that worked it out for all of f of r, you actually start seeing the patterns and you start seeing the recursion relationships. And then you can actually, the Sturm-Liouville functions, there are many good ways of actually putting them on a computer. And so eventually what I did for the star, which nobody else had managed to do, was work a computer program that will actually analytically compute the integrals. Mathematica couldn't do it; it was too slow, right? Its engine wasn't. So I actually wrote a C program that actually did the sort of basically, and it wasn't just for loops. It had the classes that actually like had integral identities and knew what they were. It was fun. I learned a lot. But yeah, so anyway, people have gone. In the 17th or 19th century, they became famous. The one that sort of worked out all the properties of a certain function, that was their bread and butter. And then it sort of stopped in the 20th century. And then there's been a number of people that have actually gotten some very nice new results out when they actually went to the challenge of finding very rapid ways of actually computing integrals like that. So there are new results, very cool ones, of how you use algebra and structures and continued fractions to actually compute integrals and properties of these functions. The one thing I wanted to say about and I just want to finish with this, that Dubsky's talk, where they had this shattered cathedral where they actually wanted to find, to place all these pieces in the thing. In order to do that, what she showed pictures of, the Fourier decomposition that you would have done in class, where you take the image and you have the various Fourier modes. And the high frequency ones capture basically the edges, the low frequency ones capture the average. And you can do things like, you can learn information from, the frequency transform. The problem with the Fourier transforms is if you have a square and you shift the square, the modes are completely different. If you decompose them into this thing, right, and you rotate it, it will be a relationship between the coefficients in sine and cos. You actually basically can fix a rotation with changing the one coordinate. And so in some sense, a composition, if you use this Bessel composition, because whatever you can do with Fourier, you can do with Bessel. Okay, people are just less practiced in doing it, and the algorithms are sometimes not as fast. But I actually think the Bessel, they have fast algorithms for the Bessel functions. So just as I represented that curve with a series of Bessel functions, you could also do it with Fourier. And so what she actually used was an image decomposition program which wasn't Fourier, but which respected the symmetry. And I think she actually was using this, just looking at the images, because the images you can then see, she showed some of the images of the different projections. And the artifacts were similar to those pictures of the Bessel functions I showed you earlier on. So that's the reason for my guess. But it's sort of interesting to see how that actually came to the fore as well. So there, I think in your course, and that's right, you'll learn mainly the Fourier stuff. But no, there are other image decompositions that can be done and are useful and are actually used by very, very few people. Most of the people just use Fourier. But yeah, if you want to do others, you're using this theory. Right, test on Tuesday. Let's just stop recording.